Hi GOH, this is Unit 3, Lesson 5, and today we're going to do proofs with partitioning. So a lot of times when we're doing these geometry proofs, we're going to need to add or subtract either angles or segments together in order to prove the side or the angle that I actually need for the proof. So if you remember back in the beginning, some things that we talked about, the whole is equal to the sum of its parts. Although that's true, we generally don't use that in our proof. That's a step that's allowed to be sort of skipped. Definitely we're using the addition axiom, and that's equals added to equals result in equals. And the subtraction axiom, the same as addition but with subtraction. So equals subtracted from equals result in equals. And substitution we'll definitely use. Equals can be substituted for each other in any equation. So the one that we're generally not using is that the whole is equal to the sum of its parts, but the three others we definitely will use. So let's show you what that looks like in a simple proof. So we have statements on the left, reasons on the right. And this diagram I have that AB is equal to DC, but I actually want to prove that AC, the bigger part, is equal to BD. So this is what I want to prove. I want to prove AC, this whole segment, is equal to BD, this whole segment. So I know the side pieces are congruent. I'll mark those in orange. I have this piece right here and I have this piece right there, but I'm trying to prove the whole yellow one and the whole green one. So the first thing that I start with is always my given. I know that little piece on the left is equal to that little piece on the right, and that's my given. But I want AC. So in order to get AC, I got to take AB, which I already know, and add on BC. I also want to get BD. BD is BC plus CD. So again, I'm adding on BC to CD on the right. So I have to add on BC to the left, and I have to add on BC to the right. So BC has to be part of my proof. And the way I get it to be part of my true proof is I say BC is equal to itself. And then basically what I'm doing is, now you wouldn't generally write this, I just want to show you. I'm taking AB, which is this piece, and I'm adding on BC, and together that equals AC. And on the right, I'm taking CD, this piece, and I'm adding on BC, which gives me that whole green piece. And I have AC is equal to BD, and that's step 3. And that is just addition. Done. So yes, I could do this a little bit more complicated and say AB plus BC equals AC as part of a step, and that would be the one the whole is equal to the sum of its parts, but that's what we're allowed to skip. And just go right to addition. As long as you're taking two things that are equal and adding on two things that are equal, then you're good to go. So it definitely can be a little bit more complicated if you have angles and those angles are overlapping each other. So in exercise 2, again, I have my statements on the left, I have my reasons on the right, and I know that SU is perpendicular to SW and ST is perpendicular to SV. We know that perpendicular lines form right angles. So the very next step is to say which angles are right angles. So I have two angles that are going to be right angles. So let's look at my picture to see what's a right angle. So SU, which is right here, is perpendicular to SW. So I did that in purple. So basically angle WSU is a right angle. And my second right angle is formed by ST being perpendicular to SV. So angle VST is a right angle. Again, they're right angles because they were perpendicular lines. So that's just definition perpendicular lines. And remember, right after I say that they're right angles, then I just say they're congruent to each other. Because if they're both right angles, then they're both equal to 90. They have to be congruent to each other. So angle WSU is congruent to angle VST because all right angles are congruent. Okay. and I was trying to prove that angle 1 is congruent to angle 3. So angle 1 is here, and angle 3 is here. I know the purple angle is congruent to the red angle, but I just want 1 and 3. So if I just want 1 and 3, then I'm going to really have to get rid of this middle angle here, angle 2. I'm going to take angle WSU, the purple one, or blue one, subtract that angle 2, and I'm left with angle 3. I'm going to take that red angle, VST, subtract out angle 2, and I'm left with angle 1. So the thing that I am subtracting out is angle 2, and if I'm going to subtract that out from both of them, I have to put it into my proof. So I say angle 2 is congruent to angle 2, reflexive property. And then I'm just going to take WSU and subtract out angle 2, and I'm left with angle 3. And I'm going to take VST and subtract out angle 2, and I'm left with angle 1. So that is just subtraction. We're not going to do it here, but just to mention to you guys, it will probably come up, but not often, is that complements of equals are equal. So if I have two angles that are complementary, the complements of equals are equal, and the supplements of equals are equal. All right. Flip over to the next page. The next page at the top is just talking about how we're going to use partitioning, but we're really not, because we're not using that whole is equal to the sum of its parts. We're just going to go right to addition or right to subtraction. But it definitely can become challenging in proofs where they're overlapping and a lot's going on. So let's look at this exercise right here, exercise 3. I know that BC is congruent to FD, and I know that angle 1 is congruent to angle 2. Okay, oh, and I also have AD is congruent to EC. All right, so I got a lot. Angle 2, I'm writing it down, then I'll go to my picture and I'll mark it, everything. So that is my given. All right, so these two triangles are overlapping. Angle 1 is right here, and it's congruent to angle 2, but angle 2 is actually part of triangle ABD, and angle 1 is part of triangle EFC, but that's nice. I have BC, which is this little tiny part here, congruent to FD, which is this little tiny part, and I have AD, which is this whole side right there. Okay, so that's good. That's a whole side. Congruent to FD, no, which one? AD is congruent to EC. Sorry, this one. So the only problem I have right now is that I don't have the whole side. And if it's helpful, you can sort of take these triangles out and redraw them so you can see what you have. So what I have is I have these two overlapping triangles, but if you wanted to redraw them not overlapping, you have this angle congruent to this angle. That's my angle 2 and my angle 1. I have this side, AD, congruent to this side, EC, and I have this tiny part of that bottom side congruent to this tiny part of that bottom side. So really what I need is I need to get this whole bottom congruent to this whole bottom. So I know BC, the left little piece, but I want to get the whole thing, so I'm going to add on CD to BC, and I'm going to add on CD to DF. So I'm going to say that CD is congruent to CD, because if I want to add it on, I need it to be part of my proof. You don't have to separate the triangles, but I thought it might be helpful for you guys to see what's going on. I'm going to take BC, and I'm going to add on CD, and that would give me BD. And I'm going to take FD, and I'm going to add on CD, and that would give me FC. And that's just addition. Now I have the whole side congruent to the whole side, so my triangles are congruent to each other by side angle side. So triangle ADB is congruent to triangle ECF. Side angle side. And once my triangles are congruent, then all of the corresponding sides and angles are congruent. And I was trying to prove that AB is congruent to EF, so that would be my CPCTC. Corresponding parts of congruent triangles are congruent. So overlapping triangles can be a little bit more challenging. And also triangles that in the next one, I have multiple possible triangles that I could be trying to prove congruent. So the important thing is to sort of look at what I'm trying to prove. I'm trying to prove MQ congruent to RQ. MQ is part of this triangle right here, MNQ, and RQ is part of this triangle right here. So that's essentially what I'm going to prove. I have some extra information though. So I know that angle MNP is congruent to angle RPN. So MNP is, maybe I'll get like red to do that. I know that this whole angle here is congruent to this whole angle here. Okay. Maybe I'll highlight the triangles that I'm trying to prove. I'm trying to prove this triangle right here, the orange one, congruent to this green one. Those are the ones I'm going to prove. So by the fact that I have that red angle congruent to the red angle, it's not even in the triangle. So I'm probably going to have to do some subtraction to do this. Besides that, I know that angle 1 right here is congruent to angle 3. That's also in the given. And I know that QN is congruent to QP. So QN is this part right here is congruent to QP. All right. So as I said, I know that whole red angle is congruent to the whole red angle, and I know the bottom angle 1 is congruent to the bottom angle 3. But remember, I'm trying to prove the orange triangle congruent to the green triangle, so I really need angle 2 right here congruent to angle 4. Well, if I know the red angle is congruent to the red angle and I know 1's congruent to 3, I'm just going to take the red angle, which was in the given, this angle right here, and I'm going to subtract out angle 1 and angle 3, and I'm left with angle 2 is congruent to angle 4. And that's just subtraction. I already have this side, and how about 5 and 6? I'm going to call these. 5 and 6, remember what those are called? When I have two lines that intersect, those are called vertical angles. So angle 5 is congruent to angle 6. And the reason is vertical angles are congruent. Now I actually have enough to say my triangles are congruent. So triangle MNQ on the left, that orange one, is congruent to triangle RPQ, the green one. The reason that they're congruent is angle side angle. And once my triangles are congruent, all of the corresponding sides and angles will also be congruent, and that is my CPCTC. Okay, so you can see our proofs are definitely getting a little bit more challenging, and we'll practice